We'll continue our discussion of organic reaction mechanisms by discussing proton transfer and rearrangement. So our learning goals for this video are to talk about the role of proton transfer and rearrangement in organic reactions. And I'll remind you that we outlined four fundamental organic mechanistic steps in the previous video, and we treated nucleophilic attack and loss of a leaving group there, so this time we're focusing on the last two, the rearrangement and the proton transfer. So let's see what we can learn about rearrangement and proton transfer. In a rearrangement, the net result is the movement of a hydride or an alkyl group. Now, I call this a hydride, not a hydrogen. It's a hydrogen with two electrons that are moving from one part of the molecule to another, and that's going to be important. So this is basically an example of a rearrangement sort of reaction. Now, most of the time this is happening in carbocations. So I want to give you this chart that tells you the relative stability of different carbocations. So how do we read this long list? Let's start at the right-hand side. First of all, anytime I've written an R, that stands for some kind of carbon-containing alkyl group. So now if I create a carbocation that has three alkyl groups attached to it, that would be a tertiary carbocation, and that is the most stable of the carbocations. By having the three alkyl groups there, it allows the electrons to delocalize somewhat, allows the charge to delocalize somewhat, so that stabilizes the overall ion. The next most stable is the secondary one, where we might have two alkyl groups attached to the carbon and a hydrogen, and again it has a positive charge on that carbon, and we would call that a secondary carbocation. If we remove one of those alkyl groups and replace it with a hydrogen, we would then have a primary carbocation. And finally, if we don't have any alkyl groups, we just have three hydrogens attached, we would call that CH3. That actually is very unstable, and it has been very difficult to isolate that in any environment in the laboratory or otherwise. So what I'm getting at with giving you this list of stabilities is that a lot of times the rearrangement occurs in order to achieve a more stable entry in this list. So we might start with a primary carbocation and undergo a shift so that it can become a secondary carbocation. Now let me show you an example of this. So here's an example of a shift that actually converts a primary carbocation into a tertiary carbocation. All right, so let's look at this in detail. The positive charge is on the right carbon. It has two hydrogens attached to it, and it's attached to another carbon which has more structure around it. Now, what will happen in this rearrangement is the hydrogen will move from the carbon on the left to the carbon that has the positive charge. When it moves, it will take its bonding electrons with it. That's why it is called a hydride transfer. So when it takes its two electrons with it, it's going to leave a positive charge behind on the carbon that it left. So the result of this is to leave a positive charge on the other carbon and to populate the carbon on the right with three hydrogens. So it becomes basically a terminal methyl group there. But notice that the place where the positive charge is now a carbon that is attached to three other carbons. So it has become a tertiary carbocation. What you will look for to recognize a rearrangement like this, especially when it's occurring in a carbocation, is the location of the charge should change from one carbon atom to another in the molecule. All right, let's quickly look at proton transfer. We've already covered a lot of this in Module 5 when we talked about acids and bases, but it's essentially the relocation of an H+ between two species, so it's an acid-base reaction. And in essence, it's a single displacement. So to remind you what that looks like, I have a nucleophile, which in this case would be a base coming along and reacting with HA, which will serve the purpose of being an acid. Then it would appropriate the proton for itself, and we'd form a new bond between the nucleophile and the hydrogen, the proton, and it would leave a negative ion behind. Now, this looks a lot like nucleophilic attack, but I want to warn you, don't confuse it with nucleophilic attack, because in nucleophilic attack, we always create a new bond between two heavier atoms, like carbon and carbon, or carbon and nitrogen, or carbon and oxygen. In proton transfer, we're always creating a new bond to hydrogen. So that's a way that you can distinguish these two from one another. Now, this actually has an important role in acid and base catalysis. So for example, acid catalysis, the initial step is a reactant being protonated by the acidic environment. for example. So here's what that might look like. Our reactant in this case is an amine. So it's an alkyl group attached to an NH2. And that's the thing that we want to have a reaction take place. And I have an acidic environment, which means I have hydronium ions in it. So what will happen is the hydronium ion will stray over there and it will undergo a proton transfer to that amine. It's actually a primary amine as I've drawn it there. And the result of that will be to create an alkyl ammonium ion. So in other words, the proton has attached itself to the nitrogen. Now the nitrogen no longer has a non-bonding pair of electrons, but it does have a positive charge. And the hydronium ion now has just been converted to water. Now I've drawn a suggestive red arrow there because oftentimes what will happen now, this is a proton transfer, what will happen next is that ammonia will dissociate itself from the rest of that alkyl group, which is now a carbocation, and so this is an example of loss of a leaving group. So in essence, what's happening in acid catalysis is it could be multiple principal steps that are happening, but the first step is a proton transfer, which can then be followed by other subsequent mechanistic steps. What about base catalysis? Well, in this case, the initial step is a base approaching a proton, that is sitting on a reactant. So an example of that might be, for example, this alcohol, and the base is the hydroxide ion. So the oxygen there is a very strong nucleophile, and it's got a negative charge. So it's going to sweep in and rip that hydrogen off of the alcohol, and that's going to create an alkoxide ion, right, the RO minus, and also water. All right, so this is an example, again, of a proton transfer step that's taking place as part of a base catalysis. That alkoxide ion now could undergo subsequent chemistry that will convert it into something else. But the point of the base catalysis was to initiate that so that we form the alkoxide ion in the first place. Now I want to give you a chance to get a little practice with this. So what I've done is I've given you 4 steps of a reaction. And I would like for you to try to identify which of these organic mechanistic steps is represented in each of these things. Now, the possibilities are listed on the lower left. It could be a nucleophilic attack, it could be loss of a leaving group, it could be a rearrangement, or it could be a proton transfer. And I'll invite you to pause the video and I'll come back and give you the answer when you're done. So hopefully you've had a chance to look this over and to reach some conclusions about this. What about that first reaction? Well, we see that it's a hydrogen bromide reacting with an alcohol, and the end of the process we have a protonated alcohol and a bromide ion. So in effect what has happened is a proton has moved from the acid, the hydrogen bromide, over to the alcohol. So this would be a proton transfer step. Okay, what about the second reaction? Well, in this case, I have an extended alkyl group that's attached to an OH2 with a positive charge, and the result is to create a carbocation with H2O. So clearly the H2O has broken off from this alkyl group, so this would be loss of a leaving group. Okay, and the third step, what do I see there? Well, I see 2 very similar looking species, but the main difference is that the positive charge is on an outer carbon atom in the first species, in the reactant species, and it's on the central carbon atom in the resulting species. So what has happened here is a carbocation rearrangement, and we've gone from a primary carbocation on the left to a tertiary carbocation on the right. Finally, that tertiary carbocation may run into that bromide ion again, and we'll end up with an alkyl bromide. What is this? What is this reaction step? Well, the bromine is acting as a nucleophile, and so this is a nucleophilic attack of the bromide ion with that carbocation. So let's summarize what we know now about organic mechanistic steps. Nucleophilic attack is going to result in the formation of a new bond to a carbon on a reactant. The loss of a leaving group is a dissociation of a bond between carbon and another atom. A proton transfer involves the transfer of a hydrogen from one species to another, but it transfers without its electrons. So it'll form a new hydrogen bond to whatever base is there as a nucleophile. And finally, carbocation rearrangement just moves the positive charge on a carbocation to a different carbon. Hope this makes sense, and hope this allows you to recognize these steps when you see them in different mechanisms.